Good afternoon, everyone, and thanks for coming out for another edition of National Museum of Industrial History's Virtual Museum. We're joined again today by Mike Piersa, who's the NMIH historian, who's going to be talking about some of the artifacts in our collection today. So since we can't be in the museum and even the public doesn't usually get to see some of the inside of our collection storage facility, this is going to give you a kind of idea of what we have behind the scenes and not inside the museum. So it's kind of a nice look inside of our archives so you can learn about a little bit about what we have in our collection and what we do outside of the museum. If you're watching this program today, you know that you're watching it for free. And if you're able to, right now the museum is closed or can't have anybody in the museum. There's a couple different ways that you can help support us while we're, our doors are shut. And you can find more about those at our website at NMIH.org. Or in a couple minutes, there's going to be a link in the comments down below that can take you there. Some of those include either just making a donation to the museum, buying a membership, and we actually have a program that we're going to be announcing tomorrow where retroactive to March 14th, any membership purchased, we're also going to give a free membership to a member of the St. Luke's University Health Network family. So not only are you helping support the museum, but you're also giving a membership to a family of healthcare workers who have been supporting our community throughout this virus crisis. So click the link down below or head to our website at NMIH.org. And just real quick, I want to touch on one other thing, which is the other program that we have coming up. Mike's going to talk a little bit later about some of the program. We have a series coming up of 3 different talks. And we also have a lot of great children's programming, and that includes a program that we just put online last week, which is our virtual summer camp. So if you're stuck at home, your regular summer camps are canceled. The NMIH summer camp that we had planned can't go on as it was planned. We actually have this online program that's actually going to be hands-on. So you can find out, again, more about that at our website at NMIH.org, or click the link that's going to be down in the comments in a few minutes. But without further delaying him, I'd like to introduce Mike Piersa. Again, he's our historian at the museum. Been with us for about 17 years now in different capacities. He oversees a lot of the artifacts as well as our collections team and our curator. So he's going to talk about some of the things in our collection today and give you an inside look into the museum. Thanks for joining us, Mike.
Thank you for having me, Glenn. I'm going to begin the screen share right now. So you should see my presentation in just a moment. So my talk today is about the different types of pumps that we have in the museum's collection. A lot of these really aren't on public display. There's one that we bring out for special events and more that we'd like to show off in the future. But when people look at these, they're easily mistaken for like big electric motors, big chunks of metal. But there's really a fascinating story behind these things, and we wanted to tell you at least an introduction to this. Again, this is just an overview. One company alone, like Worthington, that made some of our pumps. You could do an entire lecture on Worthington alone, and even their successor and predecessor companies. But for now, we're just trying to give you an overview, show you where these things fit in, and show you a little bit about how they work. So some of the images show pumps that do not belong to the museum. I included these so we have a better sense of flow and continuity for the history and kind of where you can find these things. Because one of the fascinating things about some of these pumps is that even though we have museum pieces, there are sister pumps that are still in service to this very day. So I wanted to start the presentation with this photograph because this is how you encounter a lot of these pumps that are still in service. Restricted area, do not enter. But when we look behind that door, what you see is a Simplex steam pump, very similar to what was being built in the 19th century. And there's still plenty of these in service today at various industries like refineries and places where you don't want to have the threat of sparks from electric motors, or you just need the sheer pushing power of steam to overcome a big slug of oil that you have to pump through the lines. It's really amazing that there's still a handful of these things out there in service, and occasionally you still have them being built brand new. But our story really begins about 2,000 years ago in ancient Egypt, maybe even 3,000 years ago. There's really no good records on it. But what you're looking at here is the first really by arguably mechanized way of pumping water. It's still hand aided, but this is shadoof. And you actually see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12 of these in the illustration here. And they're basically poles. Imagine a fishing pole, but instead of a fish at the end, you have a bucket full of water. And instead of the reel, you have a big counterweight. And the counterweight helps balance out the weight of the water. So you can much more easily dip these things down, raise them up to the next level, kind of like a canal lock, if you think about how it steps up, and just keep on repeating that process over and over until you raise the water to a higher level. So you can still occasionally find these things out in the world, but the technology is very simple, but as you can see, very, very labor intensive. So about 2000 BC, Greek mathematician Sisyphus, I might be mispronouncing his name, invented the water organ, which is the first reciprocating pump. Most of the pumps we talk about in this talk are going to be reciprocating pumps. And once we see some drawings, I think you'll understand them much better. Then around the same time, Archimedes produced the Archimedean screw, which we really don't have any complete examples of in our collection. But I think we're all familiar with the example of that revolving screw that's used to convey materials, including water. So the real advances started coming the 1400s, 1600s, and then of course into the industrial era. So 1475, the first centrifugal pump was described. And then about 200 years later, there was actually one built by Denis Papin in France. He was also very fascinating because he was experimenting with steam engines at the same time. So he was the first person to build a model steam engine with a piston, model steam piston. So you can actually show how steam would act to move a piston. And it seems like a very simple concept today, but it was a big deal back then. We move on a little bit. So 1698, over in England, Avery invented a very, very early form of steam pump. So pay attention to how this design looks, because you're going to see it reproduced later on. So you have your boilers in the background. Boilers heat up water to create steam. And what happens in this type of pump, you really have two pumps side by side. So let's look at the left side. You have a big chamber that you would have filled with water, and you have one-way valves adjacent to it. The chamber, when it's filled with water, could then be filled with steam. The steam displaces the water goes up to a higher elevation, and you eventually drain the mine out. So once the chamber has been filled with steam, the steam is allowed to cool and condense. And as that happens, the steam actually creates a vacuum, draws up the water, and then you repeat that cycle over again. And because this is an intermittent cycle, if you have two of these units side by side, you have a fairly continuous flow of water. So this was definitely technologically successful, but when you look at the efficiencies of it, I don't have any numbers in front of me, but you can just eyeball it and see that there had to be a much more efficient way of doing things. So by 1712, using the advancements of Papin's steam piston and some other innovations, Thomas Newcomen really developed the first true steam engine, and he developed it for pumping water out of mines. This is a photograph of Fairbottom Bob. That's the actual name of the engine. So you have your steam cylinder on the right, and it moves up and down a walking beam. And on the left is your actual chain that goes down into the mine that operates the pumps. This image here gives you a little bit better idea of how it all works. The wave of the pump rod pulls the piston up after the stroke, and then atmospheric pressure, because of the vacuum created when the steam in the cylinder cools, forces the steam cylinder down and the water pump up. So again, very inefficient compared to modern designs, but it used the power of steam and its heat to actually do work. And they were able to get these mines operating below water level, and really helped spur the Industrial Revolution, because you could get to a much larger supply of coal from that point. So here in the Lehigh Valley, they had an enhanced version of this type of engine. They used the advancements of James Watts to not rely on atmospheric pressure, but on the pressure of steam itself to push the piston, and in turn that moved the walking beam up and down. And then on the middle right of this image, you can see that long wooden rod. That's the actual pump rod that reciprocated up and down with this giant steam engine. This engine is long gone, but it was the largest steam engine in the world when it was produced in 1872, and it worked a zinc mine just south of Bethlehem, and it was capable of pumping over 24 million gallons of water a day. That would be about 17,000 gallons every minute, and pumped it from a depth of about 300 feet. This is another image showing the pump end of the machine. So the steam engine is off out of the picture. And you can see how it descends with this long wooden rod going down. And then there's mechanical pumps at the bottom. Very, very simple, just a series of one-way valves that let water in. It gets displaced or pumped up. The one-way valves close, and eventually the water works its way up to the surface. And this was really an incredible water source. There were even discussions of seeing if you could take the water down to Philadelphia. That never really materialized. It just got pumped out locally. But it was an astronomical pump in its day. And because of that, it was also very, very expensive. So the mine ended up shutting down fairly quickly. It was revived, but by the turn of the century, it was shut down for a long term until being brought back to life in a new form in the mid-20th century. But by then, they were using electric pumps mounted at the very bottom of the mine that would pump the water up to the surface. So now we're starting to get into the pumps that we actually have in the museum's collection. And the first pump I want to show you is actually a little tiny pump. You can't even see it in the museum because it's on the backside of an artifact. But it's on a machine that's on loan from the Smithsonian Institution. It's an 1877 Frick Eclipse portable steam engine. This engine was used in sawmill service in Virginia until 1901. At that point, it was actually parked in the basement of the Clore Chair Factory in Madison Courthouse, Virginia, and ran there until 1949. It's a 10 horsepower engine, which is about right for the size building you see there. If you're not running every single machine at once, you could drive a handful of machines as needed with the engine. This is typical practice, of course. Every shop is different. And then also use the steam for other purposes. If you look at some of the chairs that they built, you can see there's beautiful curves inside of them. And that happens because you take boiling hot water, dip the wood in it for, I've read, 2 weeks, and they'll make the wood pliable enough that you can actually put some really amazing curves into it. But to do that, you have to have a really, really hot source of water, which comes from the boiler. You can also do seam bending. That's a very common practice. And this is what the actual engine itself and boiler looks like. So with any boiler, you have the question of how do you get water into it? And that's what we're going to talk about with this engine here. This is a Frick, and they also evolved to building traction engines. So the engine back there was just on wagon wheels. It was towed around by horses, eventually parked in a stationary position. But not too long after that, you saw the portable engines evolved to have gears down from the engine to the wheels. And by then you really had a tractor you could drive around. So this is a drawing showing how the tractor engine was set up and how the pump works on it. So you'll see the steam cylinder on the right, flywheel on the bottom left with the clutch. And kind of in the middle of the picture, you'll see pump rod. This will make more sense when I show you an actual photograph. We can see water comes in, the pump moves back and forth, pumps the water out of it, and actually pumps the water through a feed water heater. That way the water goes into the boiler already warmed up, and the exhaust from the steam engine warms up the water. So it's a nice way of utilizing that waste steam. So you can see the silver rod down at the bottom of the picture. That's the pump rod that goes into this pump on the right. And all it does is just go back and forth all day long as the engine turns. This is another image showing how that's actually set up, where you see that 90-degree pipe just blocking the word Eclipse. That's where your water would come in. You have a control valve. Then you have your pump to the left. To the right, you have this air chamber. Because the pump is single acting, you get a fairly irregular flow of water. So to even it out, you have an air cushion inside of that dome, and that gives you a much smoother flow. Now, the problem with a steam engine like this is the demand is not continuous all of the time. If you're going to be running one machine, you don't need to throttle the engine as highly. And that would be, of course, done automatically by the governor. So if you have less steam going in, but the engine's still turning the same number of revolutions, you're going to have more water than you need, and that would overflow your boiler and cause some problems. We actually have a bypass valve, which you see just closer to the photographer from the air chamber there. And you can actually open that up, drain some water out, control the flow, and then you can get lower flow into the feed water heater and then into the boiler itself. That way you can maintain the more constant level. This is another view showing how the piping loops around and comes to a check valve and then the 90-degree valve, and that's where it actually enters the boiler, just to the left of that. So it's a very simple, very reliable setup. Steam locomotives had the same types of pumps in the early years, but they quickly evolved past those to use injectors. Injectors are really a lecture in themselves. So we'll move on to mechanical pumps and stationary applications for our museum. That engine saw service until 1949. Then the current boiler that they still use is seen here. And one of the genius things about these systems is, especially like a place like a chair factory that makes wooden chairs, you can take the scrap wood, feed it into the boiler, make steam, and aside from the capital investment and some maintenance, you basically have free fuel for it for practical purposes. So this is an image from the 1876 Centennial in Philadelphia. One of the main aspects of our museum is a reproduction of Machinery Hall, which was a giant building in Philadelphia at the Centennial that had 8,000 machines, miles of line shafting under it. But one thing we can't do here at the museum, indoors at least, is reproduce one of the more spectacular elements of that, which is the Cataract, they call it. It was a room where all of these pumps pumped water into a 10-foot deep, 160-foot long pool, which had a 35-foot tall waterfall at one end of it, 40 feet wide. This was a great place to cool off on the summer's day and also see just how powerful this machinery really was. To be back in 1876 and see a man-made waterfall really must have been quite stirring to those visitors. So there are a whole variety of pumps displayed there. I wanted to start at this one because it really harkens back to Savory and his really early pre-piston pump, 1698. This is a pulsometer steam pump. Those started coming into being in the 1870s, and they worked on the same principle that the Savory pumps did. You use steam to displace water, then the vacuum sucks more water in, and the cycle starts over again. And there were two chambers, so you had a fairly consistent flow of water. These are, of course, were much smaller than Savory's pump. You can get an idea of the scale from the bricks behind them. And these were very popular in mine uses, because if you think about a coal mine and how water and other substances leach in with it, coal dust, rock dust, slurries, mud, it's not very friendly to a pump. So the fewer moving parts you can have in the pump, the better. All this one really had was a valve that would go back and forth. Otherwise, it was really the check valves and the action of the steam displacing in the vacuum working inside the pump. This is a view on the inside. You can see one chamber filled with water, getting ready to leave, the other being filled with steam on the right. The two valves at the bottom, valve at the top that would direct the steam flow automatically. And you had a very simple pump. But again, simplicity sometimes comes at the cost of economy. So when you look at what you would have found at the Centennial and later years, you really saw a wide variety of mechanically operated steam-powered pumps. This is just a sampling from a typical trade journal of late 19th, early 20th century, and there would be page after page of different types of pump designs. Anything from a little boiler feed pump you see on the upper left that might be mounted to a steam traction engine, to giant pumps that would go on for tens of feet. These things really ranged in size depending on what the application was and also design. You have some pumps, like you see the middle one is a plunger pump, when you look at some of these drawings, you'll see the traditional design has like a traditional piston ring that seals against the pump. But if you're looking at a mine service with gritty water, those piston rings are going to get eaten up pretty fast just because you're pumping really, really lousy material through them. But if you have a plunger pump that's sealed from the outside and all you're doing is displacing the water using this sheer cylinder that just goes back and forth, a plunger basically, you have much fewer parts. You actually have no parts past the sealing ring that have to be renewed. So it was much better for those harsh services. There's a wide variety of pumps. This is a fire pump. Again, not in our collection, but I want to show you just the different varieties of these. So this is actually still locked away in the paper mill in Pennsylvania. It's amazing where you can find these things. If you go to the silk mill that was renovated in Easton, Pennsylvania on 13th Street, there's one that's on display near the powerhouse there. And these things were kept ready to run at a moment's notice, because if you had a fire in your building, you had to be able to get the water pumped up to that sprinkler system or hoses and put that thing out ASAP. So you can actually look at the nameplate on here, Underwriter pump, and they were made by different manufacturers. And they're talking about the insurance underwriters, because if you want to have your building insured, the underwriters were probably going to demand that you have a pump like this to keep your fire system in good shape. Capacity 1,000 gallons, speed per revolution 70 RPM. There's no like spinning parts on this, but they still talk about revolutions as strokes per minute. And of course, the sign, never let the steam get below 50 pounds, because you want to make sure you have an adequate steam pressure to pump that water up to whatever reaches of the building you have to get it into. So this is a cross-section showing what most of our pumps at the museum actually look like on the inside. This is from Worthington. He's the guy who really pioneered this technology. When we look at those early pumps, like the pump on the Frick engine, or the President pump, those are all engine-driven pumps with flywheels, and they all only function when the engine is actually turning. So if you have a service that's intermittent in nature, like let's say Henry Worthington, he invented this on a canal boat, because the canal boat, if it was moving and had your engine turning and your pump that was directly connected would be pumping water whenever the engine turns, that's great when you're underway. But if you're going through a canal lock and your engine can't turn and you have to put water in your boiler, what are you going to do? The only alternative at that time, without running the engine, which you really could not do in a canal lock where you're in a confined space, was to have a hand pump. And if you look at some of the capacities listed for these mechanical pumps, there's no way you're going to keep up with a hand pump without becoming exhausted very, very quickly. So Worthington in 1840 devised a mechanical means of pumping water independent from the engine. Just as a statement like that, it might not seem like a huge deal, but it was really revolutionary. So this is a cutaway view showing what a typical Worthington pump would look like. This is after he had evolved and created the duplex pump in 1859. The early ones were simplex pumps. That means there was one steam cylinder, a piston rod, and a water pumping cylinder. Those worked, and they're still in use today in a variety of applications, but it's really a reciprocating motion. So think about the handsaw. You're sawing going back and forth, starting and stopping. When you're doing that with water, the water tends to vibrate the pipes and cause all sorts of issues downstream, which can be very expensive in the hydraulic system and very dangerous in other places, like especially like an oil system or oil pipeline network. You don't want to have the vibration from the pump causing those fittings and pipes to break. But if you have a duplex pump, which is basically two pumps in one, where they're offset about 90 degrees like wheels on a steam locomotive, you always have one pump that's in motion, so you have a much smoother flow of water. And when you combine that with an air chamber, like you saw on the Frick pump, then you have a pretty uniform stream of water coming out of that pump, which is really what you want on your piping systems. So the way these things work is you have your steam coming in. I'm sorry, I don't have a pointer or a mouse I can use. That's why I like to do these presentations in person, and I can actually show you the artifacts too. But you have steam coming in to letter E, and then it's directed around what they call a slide valve to either side of the piston, whichever side you want to push on. That pushes the pump plunger, and then from area C, you have water coming in, and it's coming in against spring-loaded valves. That's what those little pyramid-shaped things are inside the 1, 2, 3, 4 valves at the bottom there. Water comes in above them. Because of the spring, the valves close after the water has filled the chamber. The pump, which is B, moves back and forth. It displaces the water, pushes it up into chamber D, again, past one-way valves controlled by springs. It acts against the springs, goes up into the chamber. And as the pump makes its return stroke, the springs fall back. Water flows in from C, and then the process starts all over again. The pump is divided in half, and then you have 2 of those pumps. So again, you get a really nice flow as this thing is moving. Now, those of you, again, this is a highly technical talk, but when you look at steam engines, most of you who are familiar with how a steam engine works notice that those little slots that go from E to the main cylinder around the piston A, normally there'd be 1 slot on either side, and the valve up there would control whether that was receiving intake steam or exhaust steam. But what's interesting about these little pumps is that because they don't have a crank on them to control how far the piston actually travels, you have to have a means of stopping the piston so it doesn't collide against the cylinder head. So the way they got around that was they have 1 port. That's what those little passages are called. There's 2 on either side of the top of A. So you have 1 port on the left for your incoming steam, and then the one closer to the middle is for your exhaust steam. And if you imagine that piston moving back and forth, as that exhaust port gets closed, and your intake port is closed, that gives you a little bit of a cushion, so that steam helps stop the piston. And then when the valve is actuated to the other side to open up, you'll start the process all over again. And if things go smoothly, then the pump will have the piston stop before it hits the cylinder head. And if the pump is pumping water, that's usually never an issue. But if the pump runs out of water and there's no water available for it to pump, then sometimes even with that cushion, the pump will just run away because it doesn't have a load. And that piston A will actually pump up against the head. It can actually fracture it. And that's not an uncommon occurrence. So if you find an old steam pump in a factory or another museum and you don't see a nice cast head on it, but you see something that's welded up or you see something with pipe plugs in it, that's probably because the pump ran away, the piston struck the head and did some damage to it. So I want to talk about a little bit how these things are actually controlled. In some cases, you simply turn a throttle valve on and off, and that's all you really have to do. When the pressure in the tank, if that's what you're pumping into, exceeds the pumping capacity of the pump, then it'll just stop. And then when the pressure gets lower, the pump will start up again. But in other instances where you want to do something like control the feed water level on the boiler, and you're not going to have an engineer sit with that pump all day, you can actually do it automatically. So this is a shot from the Wilmington Water Works in Delaware, and they actually have their boiler is still intact, and they have this probe up at the top of them. And there's actually a hydraulic fluid inside of that. And the hydraulic fluid is heated by the steam or cooled by the water, depending on where the water level is at. So when the steam warms up the probe because the water level is getting low, and therefore there's more steam inside the boiler and you need to raise the water level, the hot steam will actually make the hydraulic fluid in there warm up. The hydraulic fluid will then expand inside a pipe, and that pushes down a little valve. And you can see that valve as the silvery colored piece at the top of the picture. And that's actually what controls the steam on and off to a pair of steam pumps. And those pumps supply feed water to the boiler. Once the boiler had a water level reaching the proper height, the water would cool the probe off just enough that that valve would retract and slow or turn off the steam pumps. And it would just keep doing that all day long, around the clock for weeks, months, years at a time. And these pumps were very reliable. There's a story of one pump that somehow got bricked in at a factory, and 30 years later, somebody went to tear the wall down, and the steam pump was still running back there. It was leaking steam, but it was still functioning. This is just a close-up of that valve, showing how it's controlled automatically from that hydraulic line coming down from the top, and the actual valve at the bottom middle of the picture there. And then below that is a manually operated valve, so you can shut the steam off completely if you need to. There's also some other techniques for controlling these steam pumps. This is a drawing by Alex Carnes showing how you would adjust the steam and stroke on a larger pumping unit. There's actually little valves on the steam chest that control how much steam goes through those valve passages and actually reaches the piston. By allowing more or less steam in, you can actually control the speed. And that was very important in things like fire pumps, where you might have a small fire and you only want a little bit of pumping action, or you might have the whole building engulfed and you need to open that thing wide up and get as much energy as you can. So these are two pumps that we have in the museum collection. These were built by the Cameron Steam Pump Works. Those of you who live in the Lehigh Valley might remember the Cameron name because they were actually acquired by Ingersoll Rand. Trying to find my notes on it, but Cameron went into business in New York City around 1860 at a building on 22nd Street and 2nd Avenue. And anybody who knows that area today can see why he's not there anymore. In 1909, they actually moved the company to Phillipsburg, New Jersey after they were purchased by Ingersoll Rand. Ingersoll Rand was famous for building rock drills and mining equipment. So if you're going to be starting a mine up, of course, you're going to need a drill to drill through the rock. And odds are you're going to drill deep enough that you encounter water. So if you're buying a rock drill from them, why not buy the pump too? So these pumps are Simplex pumps. But what's really unique about them is, other than that piston rod, you don't see any moving parts on these things. So if you're going down into a coal mine or someplace with really bad water and a lot of abrasive material, this is the kind of pump you want, because you don't want to have a pump like that Wilmington that has arms going back and forth and bearings that are going to wear out really quick. This is an image of the Ingersoll Rand plant in Phillipsburg in the early years, when they after they just started producing those Cameron pumps. And when you look at the serial numbers on these things, they just churn them out one after another. And these things were literally shipped all over the world. Here's a period advertisement for one of them. I'll let you guys read that on your own. But the big selling point, as I mentioned, was they don't have any moving parts on the outside. So you could actually submerge this entire thing underwater. Like if your mine had to shut down for whatever reason, this could be completely submerged. All you had to do was turn that compressed air line onto it, and it would start working underwater. That was a very important feature of these steam-powered and air-powered pumps. If you look at the New York City subway today, I've been told that they still have reciprocating air-powered pumps that work on the same principles, because if they get flooded out, you just turn the air onto them, and they'll work underwater. You don't have to worry about electrical current going in and short-circuiting things. This is what it would look like out in the field. This is an Edison powerhouse, I believe, somewhere in New York that was under construction, 1 foot below tide and 21 foot deep. So in the lower left corner of the picture, you see one of those Cameron pumps. And again, this would just work day in, day out, however long you needed it to. And what made them really unique was their internal workings. You have your steam control valve up on the top. You have your steam piston C, which goes back and forth. And if you look at the letters I on either side, those are little poppet valves. The piston would actually touch those valves, and the steam would flow through those passages and then go back up to the top of the pump, push letter F, which is a piston, and that controls valve G, which is a typical slide valve like you see in the steam engine and many of the other pumps. And then that would change the direction of the pump. The piston below would go in the opposite direction, and then would just repeat that process all over again. This is the pump end. It's very similar to the Worthington pump we saw earlier, but the advancement that Cameron made was he had a screw at the top, and you could actually unthread that, and then both valves would pop out. You could service them very easily, replace them very quickly, and be in business. Because every minute you weren't running these, this was water filling up your coal mine or quarry. So you wanted to keep these things in service as often as you could. One of the other prominent makers we have here at the museum is Knolls. He began building steam pumps in 1858 when he was operating a warping mill in Warren, Massachusetts. A warping mill is a textile mill. When you look at fabric, you have your warp threads and your weft threads. Warp threads are the threads that, if you're on a loom, those are the threads being woven towards you. There's a joke, you have to be warped to weave. So Lucius Knolls had his warping mill, and he had a reason to develop a better better water supply. So he decided to go out and build his own steam pump. And he eventually became so successful at building the pump for himself, he had other customers and built a fairly large business. By 1879, he merged with another maker, Blake, who continued making pumps under the Knolls name. And the Knolls branched out, partnered with Crompton, and actually started building looms for the textile industry. So when you look at the museum's textile collection, we actually have multiple Crompton and Knolls looms. So it's a very fascinating connection between all these different industries. So the pump that we have is a mining pump. This is a description from their advertising. And not to make Pennsylvania look bad, but even in the 19th century, they were bragging, the pump manufacturers were, that these mines are favorite pumps in the mining districts where the worst water possible is pumped. But their claim to fame was that these pumps could handle the water very, very well. So this is a typical Knolls mining pump. You see your steam cylinder on your left. It's a Simplex pump. And then you have your pump on the right. And their claim to fame was a universal removable cylinder. And they offered a design made of phosphor bronze, which is what our pump has, which was very, very durable when you had very harsh water conditions. So what made our pump special is we actually dug it up. This is the only known steam pump to survive from a Pennsylvania slate quarry. It was found in West Bangor by crew reclaiming a quarry. They thought it was an electric motor, but we looked at it and realized, no, this is a giant steam pump capable of pumping 500,000 gallons of water a day. So we actually got this donated to us. It doesn't look like much, but it's actually starting to clean up fairly nicely. And we actually use it here at the museum, or if there's ever a quarry park built, we'd be happy to loan that out to them and let them display it in its original setting. But again, you can see that this was actually buried. It was probably built in the 1880s. But after some needle scaling and primering, it starts to clean up fairly nice. And this image here shows the Waterin, which is a real testament to that phosphor bronze line. You can see inside that bronze, despite the iron being fairly rusted, held up very well over time. And I don't think we'll be restoring this operation, but at least we can get an idea to show people what these massive pumps look like that kept these quarries dry and allow them to operate to depths of 500 and sometimes even the cases over 1,000 feet deep. So again, pumping machinery was pretty much everywhere in the 19th century, and think about it today, it's still everywhere. It's just in a different form. Bethlehem Steel used hydraulic pumps to operate their hydraulic presses. So this is a bending press that's probably going to be moved to the museum very soon. It weighs, we're guessing, around 500 tons. It has these giant hydraulic cylinders that are pumped full of water, and the hydraulic cylinder is pushed down on pieces of steel. There is wide flange beams blocking this press up right now, but it used to be that there'd be giant pieces of armor plate up to 21 inches thick put underneath that press and forged. It exerted 7,000 tons of pressure, and that pressure came from this guy. It's a steam-powered intensifier. When you look at the other pumps in our photographs, and you compare the size of the steam cylinder, which is on the left, there's two of them here, and the size of the water cylinder, you might have a water cylinder that was typically 2/3 the size of the steam cylinder. That would give you enough water pressure to get into a boiler at a higher pressure than your steam, do some work. But you really didn't have a need for much higher pressure than that. But when you look at a hydraulic press like that, you might need in excess of 2,000 pounds per square inch, and in some hydraulic applications, way higher than that. So to get that pressure differential to work, you increase the size of your steam cylinders and you decrease the size of your water cylinders. So in this press, the former chief engineer told me you had 150 PSI steam coming in and 2,000 PSI water coming out. And when you look at a machine like this, it's an outside plunger pump. You don't have piston rings on the inside. You have your packing on the outside. So you don't have to worry about those rings giving you trouble inside. You're just moving those plungers back and forth and displacing the water inside. This is not this pump here we do not have at the museum. This was at a chocolate factory that was being demolished. We can get an idea that these pumps are fairly universal in service for high pressure applications. Very, very typical design. And again, you can see it's spelled out 18-inch steam cylinder by 2-inch water cylinder. In this particular case, the math worked out to give it about 5,000 pounds of hydraulic force. And you can see the gauge over here goes up to 10,000 pounds. You typically want the gauge to operate in the middle, so 4, 5, 6,000 pounds. That's where you'd typically be seeing your hydraulic pressure. So these things could put out an amazing amount of power. And again, just to show you, we do not collect everything we see. This is only a small fraction of the pumps at that factory, and these actually got sold to a commercial user and are probably still in service at a dairy somewhere in Pennsylvania. Now, the pumps so far that we've been looking at have been single or double cylinder steam engines. They use the steam once and they exhaust. The problem with that is they're not very efficient. The steam pushes the piston until it reaches the end of the stroke, then it returns and exhausts. It's not like a steam engine like the Corliss that we have, where you can turn the steam off early and let it expand. So what makers of these pumps did to get around that without building full-fledged engines was to build compound pumps. So this is a Wilmington pump, and probably its most famous duty as a compound duplex pump, and that's for providing water pressure for the Eiffel Tower. This pump had to supply water all the way to the very top. And what it does is it takes 2 steam cylinders at high pressure steam, uses that through the cylinders, exhausts it into the second set of cylinders. Because it exhausts at a low pressure, you have to have a larger amount of that steam, a higher volume. So you have to increase your cylinder size. That's why the next set of cylinders is larger. But because you use the steam twice, you actually save between 30 and 33% on your fuel bill. So if you have an installation where you expect those pumps to be running a long time, like the Eiffel Tower or Bethlehem Steel, you're going to try to purchase a compound pump that make that initial investment up front, and it's going to save you in the long term. And right now, we're working with a donor in New York City who made that investment back in 1901, and they had a similar pump running right up until 2019, when issues not associated with the pump, which was still very reliable after being maintained all these years, was still in service. So that's 118 years of continuous service every year, not necessarily every single day. Pumps like this, because they use steam and exhaust it, are especially good in buildings in the Northeast because the steam will exhaust and you can put that into your heating system. So if you're making steam for your radiators, why not send that steam through a pump, get your water pumping done, and then you still have that steam available to do your heating work. So this is a pump that we're going to be in the process of moving, hopefully in the near future. It's a compound pump, so you see those cylinders arranged like the Eiffel Tower pumps, made by the same manufacturer, Worthington. Then you have your Waterin on the right. And it's not a coffee can on top of that thing. That's actually steam cylinder oil. That's a very thick 600 weight oil that gets pumped into the steam cylinders to lubricate them, and lubricates the steam valves too. We did some basic math on this thing, and if we took our measurements right, it should pump between 355 and 715 gallons per minute, maybe even more. So that means that at slow speed, according to the catalog, and you can run it much slower than even that, would do about 500,000 gallons a day. One of the neat things about these pumps is it's not like the turbine pumps or electric pumps where they're only happy with a narrow range of speeds. You could have these things running at a virtual crawl and they'll still be pumping water. And they can go up to about 100 strokes a minute, at least on the older steam powered pumps. So another New York connection we have is the Binghamton ferry boat. This boat was scrapped in 2017, but it ran between Barclay Street in Manhattan and New Jersey, beginning in 1905 and ran through 1967 for the Delaware, Lackawanna, and Western, and later the Erie Lackawanna Railroad. Some of you from New Jersey might remember having dinner in this boat because it was converted in 1975 to a restaurant. But steamboats, just like any giant steam plant, have to have a way of getting water into the boiler, or in the case of this installation, circulating your cooling water through a condenser, because you don't want to be taking in water from the Hudson River and turning that into steam because of the salt content. So you want to recycle your water and use it over again, but you have to cool it down using another water source. So this actually had a circulating pump on it. And when the ship was converted to a restaurant in the 1970s, the circulating pump engine was removed and placed into storage at Pratt Institute in Brooklyn with Conrad Milster, who donated the engine to us in 2012. This is a shot of its crankshaft and flywheel being lifted out of the basement. And that's the engine on board a truck heading back to Pennsylvania. So one of our projects at some point in the future is to get this thing put back together. It's missing a few parts, needs to be opened up and inspected. A wall actually collapsed and let some sand into it. So we have some cleanup work to do, but at some point, we'd like to see this thing steaming again and being one of the last remaining Lackawanna Railroad steam engines, even though it was used in a marine application. So we've been talking about water pumps so far, but we have a couple of oil pumps in our collection. This one here, we'll see the picture of the pump in a little while, was an oil pump used at the city investing building in New York City. This was the world's largest office building when it was constructed in 1908. Those of you who study Bethlehem steel history will know 1908 is a key year because in January of 1908, Bethlehem Steel introduced the wide flange beams, which made humongous skyscrapers possible. But right before that, they were still using I-beams and riveted construction. So right around that transition time was when this building was built. So it doesn't have Bethlehem steel in it. It has the older construction, but it still reached 487 feet tall, had 12 acres of rentable space in it, and we're able to house 10,000 people. This was located at the corner of Cortlandt and Broadway, and it was actually torn down in 1968. That's how the pump managed to survive. If it was still in there, it might have been abandoned in place or upgraded. But in 1968, Conrad Milster actually went down in the basement, got permission to recover it and some other pumps, and brought them to Pratt Institute, where they could live on. The site is now occupied by One Liberty Plaza, which was built as a U.S. Steel building. It's 54 stories tall. It's basically a block or so away from the World Trade Center site. So it's always been a very popular location, but this is one of the buildings that was there early on in the 20th century. And it was also a neighbor with the Singer Tower. So skyscraper fans are probably more familiar with the Singer Tower. It was the tallest building in the world at the time. And these buildings actually shared a common smokestack. So at one point in time, the boilers making steam for our pump were exhausting through the smokestack shared with the Singer building, which was also torn down in 1968. So this building was just beautiful on the inside. They called it a monument to capitalism. Again, this is a type of building you could do a whole lecture on in itself. But there are parts of it that survived on. Conrad took the pump to Pratt Institute. That's a photograph of their engine room. But what fewer visitors to Pratt got to see was the boiler room. Just scrolling through my pictures here. That's the pump as we received it. And this is one of two pumps of the same size that he actually acquired for the boiler room. These pumps were actually installed in the city investing building in 1927 as fuel oil pumps when they converted from coal to oil. So Conrad kept the pump that he gave us as a backup pump, never actually used it. So that pump's been indoors its entire life, very well cared for. And then the other pump, which is still in place as far as we know to this very day, is a sister pump plumbed into the oil system. And to give you an idea of how it's set up, you have a pair of electric pumps on the left and your steam pump on the right. The insulated pipes are for your steam going in. The smaller pipes, thicker pipes, are steam going out. You have your oil pipes on the left and your gauges, automatic devices. And then the fuel oil was fed into any of three boilers, which you see in this shot here. You barely see one off to the right, a Foster Wheeler, and two combustion engineering boilers on the left. Again, just to show you that we're not collecting every pump in the world. There's a lot of other ones out there. This is their house pump that did the main pumping for the boiler feed water. Again, saved from the city investing building. So they were doing this recycling even 50 years ago. And probably my favorite pump, the pump in a cup. It's a model pump that he was actually building. So just a few more pumps before we round up the presentation, just to see the diverse array of places we can get these things from. This was a steam-powered crane in South Amboy, New Jersey, used by Trebcon Construction in Newark Harbor. It was actually used near the end of its life in the early 2010s to help, I believe, build Brooklyn Bridge Park, where they had to do some pile driving. That's what this machine specialized in. It was built probably in the 1970s from an amalgamation of parts from all over the place at a yard near Philadelphia. And a vertical boiler in the backside, and a big giant air compressor on deck was operating in the later years. This is a close-up view of it. You can see that it's a barge mounted, so they could float it pretty much anywhere they needed to. And in a future talk, we might talk about the engine we received from underneath it. But you have your main hoisting works above, which are unfortunately long gone. And behind it, you had a trio of steam-powered pumps. This is a Worthington pump, probably used for fuel oil. I'll have to confirm that. That was given to Blue Mountain Antique Gas and Steam Engine Association. Then a smaller Dean pump. Now, what blew us away about this Dean pump is we looked at it and thought, well, it looks the same as pumps built in the 1920s, like the one from City Investing Building. But a representative from Dean, which is still in business, got back to us and said serial number 71363 actually dates to 1964 and was sold to the Todd shipyards in Green Bayou, Texas. And it was built as a fuel oil pump and could actually pump fuel oil up to 250 PSI. So it's a pretty powerful little pump. You can see a tiding here against a water pump off on the right. So our little Dean pump, we took back to Bethlehem. And we actually operate this for demonstrations to show the public just what these things look like in service and how powerful they are. We hooked up to a 5-gallon bucket, and I think in the space of, before I could even start counting, it must have been 2, 3, 4 seconds, it felt like that thing was empty. And of course, we can look up the full facts and figures, but it was just astonishing to see how fast that pump actually did the work. And then the final pump that we just acquired, which I have to be honest, isn't actually a pump, it's the turbine that drove the pump, is a Carling steam turbine. So if you look at some of those older pumps that pumped 500,000 gallons a day, they were like 9 feet long, 10 feet long. Well, this pump here is only a few feet long, 75 horsepower. If you compare that to our big Corliss engine, our Corliss is 400 horsepower with a peak of 454 horsepower. But this is 75 horsepower here, but it could still pump. Again, if you look up a typical pump sizes, about 1.4 million gallons a day, which is pretty impressive given how much you can shrink down that motive power unit. So this dates the 1950s and was only taken out of service about a year or so ago. And we'll probably use it in our front yard just to show you what the turbine looks like, turn it over, and really get a sense of the difference in size between the 75 horsepower turbine versus the 75 horsepower steam engine, which we have also on display in the yard and operate. This is a split case turbine, so you can actually take it apart and see all of the steam parts without disrupting the steam piping. Very sophisticated materials for its day, like chrome steel and turbine blading. The view of the builder's plate. 24C is the type of turbine it is. I believe it has 24-inch diameter rotor on it. And then the C is their specification in the catalog for horizontal split type casing. Again, turbines are a whole nother world we could go into. But since we've almost gone an hour with just the pumps at the museum, I think this is a good time to, if there have any questions, and back to you, Glenn.
All right. There are no questions so far, but we'll give it a couple minutes to see if anyone is out there and has any questions about your presentation. In the meantime, would you like to talk about the upcoming programs that are coming up with the lifting talk?
Yeah, very soon we actually have a trio of fascinating talks coming up from people outside of, well, I guess not me, but there's one from me and two from some people outside of the museum. Those are going to be about Alice Chalmers and P&H cranes. Tom Fearing, who's a former chair of the American Society of Mechanical Engineers Heritage Committee is going to be talking to us about Alice Chalmers and what they did in Milwaukee, Wisconsin. Alice Chalmers was famous for making giant machines for companies all across the globe. And they actually have one of their machines that they sent to Phillipsburg, New Jersey, which is half an hour from the museum. It's a 6 million gallon a day steam powered pumping engine, 51 feet tall. So Tom's going to be talking about the actual factory that built these machines and a lot of other pieces of equipment. And then Phil Beard, a volunteer with the New Jersey Transportation Heritage Center, is going to be doing a live video debut showing a tour of Big Alice, which is the nickname for the Alice Chalmers pump in Phillipsburg. And because Alice Chalmers has a fascinating connection with P&H cranes, which Tom is going to be discussing with us, I'm going to be doing a very brief mini tour of the museum's P&H overhead crane. So it's going to be a real trio of talks that tie together thematically very nice and show you some fascinating pieces of local history that were actually made in Milwaukee and help show how our museum is really national in scope and connected to a lot of other really fascinating pieces of history. So I think people are really going to enjoy that.
Excellent. I don't think we have any questions, so I want to thank everybody that joined us that's watching out there for taking some time out of your day to learn about some history. And as always, keep tuned to our Facebook page here to find out more about the events that are coming up. We have a lot of lectures like Mike just talked about, the 3 coming up, as well as our kids program. So if you have children or grandkids or know somebody with kids who are looking for some things to do, please stay tuned to our page and check out NMIH.org for more information. And thanks again, Mike, for joining us and giving us a little bit of a look into some of the other stuff that's in the museum.
Well, thank you for having me. Hope it wasn't too detailed for you guys, but I think it's good to just get this information out there because there are, I know, a handful of you who are on the edge of your seat waiting to hear what we had hidden away. And hopefully we'll get a chance to pull some of these out for visitors every once in a while and show some really, I think, fascinating pieces of technology.
Awesome. Thanks so much, Mike, and have a good afternoon, everyone.